All right. You're getting the idea, I hope, by now. We've done alkanes, alkenes, and alkynes, and it's been the same basic pattern. You're going to get the properties of each, how to make them, preparation, and then reactions of them. There's an extra step in this one. If you take a look at the very first thing, it doesn't say properties of alcohols. Okay? It actually says nomenclature. And here's the reason why. You already knew how to name alkanes and alkenes and alkynes. You don't know how to name alcohols. I mean, technically, although I did get one as part of the alkene reactions, and we did name it. And it wasn't that hard. And we also know another one that you're making over there. That's an alcohol, right? What's the name of that alcohol? No, what's the name of it, though? You know it.
Ethanol.
Ethanol, exactly. All right, so what do you do when you name these guys? You name the alkane first. First thing you do is you name the alkane and all that implies, which is a lot. All right, so if I've got a methyl or an ethyl or a chloro or whatever on there, I got to name it. I got to start from the lowest possible numbers and all that other stuff. I got to do all that stuff I always did. Dies and tries and all that. So you name the alkane. Second, you number the OH group. And you want to number them so he has the lowest possible number. Now, you might think to yourself, well, geez, what about if there's a double bond in there? Doesn't a double bond take precedence in the lowest possible number? And the answer is yes. One of the guys over the other takes precedence, and we'll learn, but not today, and not this chapter. This chapter, you will only have one functional group in a given alkane. So you're only going to have an OH on there. You're not going to have an OH and a double bond. Okay? You're not going to even have chloros or fluoros in there. You're basically just going to have an alkane or chain of some length with branches coming off of it, and an OH. Or an alkane chain of some length with branches and a double bond, and the carboxylic acid, but not at the same time. Okay? All right, so you number, give the lowest number possible. Then you add an OL suffix. You guys have seen that. Ethanol is a good example. You also saw, I also mentioned methanol, and one of the ones I made under reactions of alkenes, I believe, was 2-butanol. So you've seen this before. We just didn't get the systematic naming system down. There's one other thing you have to do. If you have more than one OL, you're going to need to put in a di or a tri in front of that OL. Okay. Good enough. So there's a step I have not had to put, but I'm going to have to put for every single thing we talk about from now on. Carboxylic acids, aldehydes, ketones, esters, ethers, amines, all of these are going to get this step because you don't know how to name them yet. All right. Now that we've got that, let me get a few examples down. Right? Example 1, I'll do just the easiest one we've already seen. What do you think this guy has to be? Just one carbon and an OH? Methanol. Yeah, methanol. By the way, a couple of little mistakes, nothing huge, but it's methanol, not methyl. There are times where you don't name the whole alkane, like you don't put methane. You put just meth. This is not one of them. You have to put the whole alkane, methanol. And you can probably figure out where I'm going with this. What happened? The ANE will change. It has a chance to change if I do have other things in there. We don't have to worry about that yet, but we will. How about this guy? Can you name him? Okay, draw him first and see if you can name him correctly. I'll give you a chance. Try it on your own. Remember, those of you who try these, when I ask you to, and don't just wait for me to give you the answers, you're the ones who are going to be learning from this, rather than just waiting for an answer. Oh, and one other thing I should mention is, especially consider I've got Jacob and Jared both in this class. We are going to have a lot of suffixes. I believe already one time it happened with one of your test questions. I don't give them back to you in Chem 2, so I don't know. One of your questions, I'm sure it was with one of you too, where I could not tell what the letter was. And if I can't tell that it's OL and not AL and not YL and not some other name, ENE versus ANE, I am not giving you points for that. You need to be more careful on your writing. There's better penmanship. I don't normally say that, but on tests, I will. All right, because these are going to be so close together. Methanol is not the same as methanol. Okay, they're a different thing. Methane is not the same as methene. It's only one letter difference, and they look kind of alike, and you can't do that. All right, so what would this guy be? I hope you all numbered it from this side. He would be 3-methyl, 2-butanol. Is that correct? 2-butanol. All right. And if you're wondering, say, well, when I write my notes on the board, I don't always write so neat. That's different. I'm not being tested. And I do, now because my handwriting stinks, I type 90% of what you have, including right in front of it. So I do take precautions to avoid that. All right, lastly, I have one more example, and this is something I actually have, stuff that's in here. What is this? Antifreeze or coolant you put into your car's radiator. All right, that is this. Okay. Now, how I would name this guy would be, it's a little weird. Listen to this carefully, okay? You ready? All right, it's a little strange. I got to put a die in front of there. Where does the die go? I've got 2 OHs. This guy is called 1,2-propane-diol. 1,2-propane-diol. Okay? Another reason why I said you have to keep the entire alkane name. Some people notice, well, do I need, here I had the E and here I did not have the E. I mean, it's one of those, just basically spelling rules. I'm not going to take off for that. If you forgot the E here, if you put the E up here, I'm not going to take off, but it does make sense. Think about it. If I follow this with a consonant, I have to keep the E in here. If I have a vowel, I don't keep the E in there. And that's kind of the similar kind of rule you would have for other things like that. You understand? If I have a consonant after propane-diol, propane-triol, I wouldn't just have propan-diol, propan-triol. I keep the E. But here I don't have to, because the next letter is a vowel anyway, and it makes that A a hard sound anyway. But I'm not going to care. Okay, as long as it's methane and propan, that's all I care about. Whether you keep the E or not, it's not as big of a deal. But you should obviously keep it for that, in that case. All right, good enough. You know how to name them. All right. Well, let's get to the properties now. Because one other thing before I meant to mention this. This is why I put that come up separately, because I always forget. On your papers, I think on most of them, although I am forgetting them on a few of them, papers that I've already given you. We haven't had any yet, so don't worry. It hasn't come up yet. But every single type of organic compound I'm going to talk about, I'm going to put down in terms of a generic formula for it. And that generic formula, in this case ROH, is going to be listed on the test. You're going to have a bunch of these guys listed as part of the, remember there's 2 parts to this test. One part's going to be the reactions. You're going to get the first of those today. You're going to get about at least 15 minutes today to work on this first worksheet. Okay? That's one part. That's the bigger part. That's about a whole period. The shorter test, about 15 minutes maybe, is going to be, one of the sections on there will be this. It'll say ROH. And it will have R, C, double bond, O, R. And it'll have R, C, double bond, C, R. And I'll ask you, what is that compound? It's just a matching section. Up at the top, it'll be all the things. ROH will be an alcohol. He's a general formula for an alcohol. Any amount of carbons, put an OH on him, that's an alcohol. This guy, you don't know this yet, but you're going to find out he's a ketone. This guy, what's that? You know that one. What's he? He's an aldehyde, right? I'm sorry, he's an alkene, right? And if I had a triple bond, he'd be a alkyne. All right, so there's going to be a section on the test, a rather large section on the test, where you're going to have all the possible general formulas for these guys. They're going to pop up, and you're going to have to actually name them all, what they are. Okay? All right, next. Well, now we're right back to where we started. For every one of these, I'm going to talk about their properties. I'm going to talk about their reactions. Okay? And I'm going to talk about the preparation and the reactions of. Properties. All right. For alcohols, what do you see on an alcohol, an OH? All right? Now, that kind of, you're going to see this as we go on. it kind of reminds you of a base, right? That is going to be, later on, when we get to esters, you're going to see how the OH acts in much the same way as a base does. Like, for example, NaOH is sodium hydroxide, right? This is the hydroxyl group, the hydroxide group, right? Well, now I just have a C in an OH. Okay, so it's similar. No, he is not basic. Okay, but he acts in a much the same way when we get to reactions. And just like bases that have OHs, they have hydrogen bonds. So basically your properties are going to depend on two things. How many of those OHs you have and how long your carbon chain is. Two factors determine this. Depends on two factors. And the main things I'm looking at, when I'm looking at properties have been so far, and they're going to be boiling points, solubility, and reactivity. Okay? Well, the boiling point and solubility is mainly what I'm going to talk about today. Let's start with the number of hydroxyl groups, the number of OH groups attached. What would you expect would happen the more OHs I put on this chain? Well, here's a good question. What would happen to the solubility if I have more OHs on there? More or less soluble in water? Think. More or less soluble in water. What's the one rule of solubility? Like dissolves like. I put more OH groups on, is it going to be more or less soluble in water? More. Why? What is OH? OH is the hydrogen bond. What does water have? Hydrogen bonds. They're polar. They're charged. They will dissolve better in each other. Secondly, what kind of bonds are hydrogen bonds? They're really strong. They're the strongest of the intermolecular forces that hold things together. So I would expect the more OHs I have, the tighter they're going to be held together, and the harder it's going to be to boil. Okay? Those are the two things. The more OH groups, the greater the polar portion of the molecule, therefore the greater the solubility of the water, and the higher the boiling point. Because they're held together tighter, greater intermolecular forces. Now, the way I'm answering this is the way you need to be able to answer it on a test, especially and included on the AP test. I have seen, going over, I think I mentioned this before, just searching through sample questions for the AP exam, I have seen, as part of their questions, their open-ended questions where they'll give you two compounds and ask you to tell them why one guy would be more or less soluble in water than the other. Well, you need to go into a lot of detail on that. It would not be enough to just say, when you're answering a question like that on an open-ended question on the AP exam, and they gave you two compounds. Let's look at two compounds. They give you these two compounds. And they ask you, don't draw this, but they ask you which one will be more soluble in water. It's not enough to just say, that one will be more soluble in water because he's got more OH groups. You need to explain it. You need to talk about, he's got more OH groups, therefore he's got more hydrogen bonds, greater polar portions of the molecule. The rule of solubility says, like dissolves like. So charged substances dissolve in charged solvents, therefore I would expect this guy to dissolve better than that guy who doesn't have as many OHs and has maybe fewer, he has fewer carbons and carbon bonds, non-polar bonds. Okay? You need to be able to explain all that. And if it asks about boiling point, all right, same basic idea. You say, well, the hydrogen bond is the strongest of the intermolecular forces, and it's going to hold these molecules together tighter and therefore be harder to boil. This will get you at least some credit on this, even if, like, for example, I've seen the kind of questions they have in open-ended. They'll be like, here's a scenario. Question 1, question 2, question 3, question 4, question 5, all about that scenario. And the first question might be an easy one like that, where you just have to explain something. And the next question might say, calculate the whatever of this. Or calculate, if this were to react with that, what would happen? And what would and you may not know those, but at least if you can answer that part correctly, you'll get some credit. Okay? All right. Second part, besides the number of hydroxyl groups, the number of carbon groups, how many carbon atoms you have. The more carbons, we've already seen this. the greater the number of carbons, when we talked about alkanes, I said the higher the boiling point. We had a whole chart up here, methane, ethane, propane, butane. It became from gases to heavier gases to liquids to eventually you get so many carbons, you got tar, okay? And it boils at extremely high temperatures. So the number of carbons, the more carbons I have, the higher the boiling point. Now that seems a little counter. A lot of times people want to say, well, hydroxyl groups and carbons, I'm going to have the opposite in both cases. You do not. Listen, the more OH groups, the greater the solubility in water and the higher the boiling point. The more carbons, the less the solubility in water, but the higher the boiling point. Boiling point goes up with the more carbons, even though the solubility goes down. Okay, so write all that down. So once again, all things being equal, the more carbons, the greater the boiling point. Again, don't draw this, but I'm going to do a couple of examples here. Okay. Predictions. Who's more soluble in water? And we'll call this guy A, call him B. Who's more soluble in water? A. Who has the higher boiling point? B. See why? A is more soluble in water because he has, ratio-wise, more OHs per carbon than this guy has, right? All right. But boiling point wise, this guy's going to be hard. Now let me just make one more change. See if you can see what you think of this. Okay. Still, now this is a little bit harder question. Probably can't ask you who's more soluble, because I purposely drew the same number of carbons in both, and the same number of OHs in both. So it'll be a tough question to ask you that. But I can ask you who has a higher boiling point, A or B. And the answer is not C.
There's B.
Oh, I meant to have the same number. Don't I have 1, 2, 3, 4, 5, 6, 7, 8? 1, 2, 3, 4, 5, 6, 7, 8. Well, I should have one more like that. Okay. All right. Sorry. All right. Now, here's the question: which one, assuming they both have the same number of carbons, is going to have the higher boiling point now? Why?
Because it's a shorter change.
No, not because of the longest continuous chain. Because what?
I said the chain. They branch off.
Branches. That look back under alkanes, and you'll see that I told you branching does what to the boiling point? Lower. Yeah. So you're going to have to keep all these things in mind. All right, and that's a lot of stuff to keep in mind when I ask you questions like that on the test. In a week or so. Okay, good enough. Properties. Now we're only going to get to a few reactions. That's why I said you're going to have about 15 minutes to get some work done today. Because we're only going to do a few, and I don't even have to do them for the most part. Where do you see what I mean by that? Preparation reactions, how we make alcohols. I have very little to write about this first one, except what's already on your paper. Why? Because this is not a general formula. All the ones up till now have looked something like this. R something plus HX yields R something, whatever. It was a generic formula, and you replace the R with however many carbons you actually had. This is a specific reaction. It only works with carbon monoxide and hydrogen, and it only makes one alcohol. You can only make methanol from this process. That's what you make. And it's already there. You don't have anything to write down. I don't have to do an example of it. That is the only example. Okay? By the way, is it balanced? No. What would you need if I gave you the specific example?
2.
Right? See why? Because you have to remember there's an H here, an H here, and an H there. Right? You have to remember that. Okay, I don't need to do an example of that because that is the only one. It's not a generic formula. It is the only formula. Now, hydration of alkenes, I don't need to do that either. We've already seen it. If you look back under reactions of alkenes, that's the first way we learned how to preparation of an alcohol. And I made that alkene. I even talked about Markovnikov's rule right after it. Remember what happens when we do an alkene. The OH goes where of the choices he has? More substituted carbon. Exactly. That's Markovnikov's rule. So if I gave you a guy like, I'm not going to make you do it, when a double bond is there, and I react him, as you will look back at that reaction, where's the OH going to go? It's going to go. Is it going to go right here? That's the towards the middle? No. It's going to go here. Of the two choices, it will go on this guy. Okay? All right. And so that one I don't need to do. Third one. Here we go. Hydrolysis of alkyl halides. This one I want to do. It's where you take an alkyl halide. Think of the word. Alkyl, CH3, CH5, or C2H5. It's basically a carbon group of some length with a halogen on it. Okay? And you react him with NaOH. We've seen him before. Sodium hydroxide. Sodium hydroxide. What's going to happen? The OH from the sodium hydroxide is going to get it switched with that X. You want to know what I'm going to do? I'm going to do a demo for you. While I'm setting this up, I want you to finish up what you can of this. Here is exactly what I'm going to take. You can look at the bottle if you don't believe me. It says 2-bromo, 2-methyl propane. And I'm going to react them with, it says sodium hydroxide. Sodium hydroxide plus 2-bromo, 2-methyl. So I'm going to take this. Oops. You all agree? Well, you put your own name down for that, although I already said it once. That's what I want you to continue and see if you can finish up that reaction for me on your paper while I set this guy up. Okay, whether you're done or not, look up here. Let me show you what I'm going to do with the demo. Put that light on for me. I think you might be able to see it a little bit better with a light on. Okay? I put this little magnetic stir bar in here. Everybody's looking here now. Okay? So that magnetic stir, I put them in here and I turn it on, and that spins on here. This thing's spinning. We've seen this before. I'm going to add some isopropyl alcohol. That's just the solvent in which this is going to take place. Okay? So I'm not, this is not the reaction. It's just the solvent where it's not really involved in the reaction. Now, I'm going to add to that. I'm going to turn it on, and I'm going to add some sodium hydroxide to it. And it tells me I need 10 drops of sodium hydroxide. So here's my sodium hydroxide. All right. And I'm going to add 10 drops to it. And maybe an extra one. It's okay. All right. Now, sodium hydroxide, as we all know, is a base. And I'm going to add some universal indicator to show you that. Okay? Here's the indicator. Although I thought I had, yeah, I do have another one. This might be able to use it all up in this one. I'm going to throw it out. It's an older one. Okay, I needed quite a few drops to show the color. Almost out, so just enough to do this. let me show you something about it. I'll add a little bit more so you can see the color a little bit better. All right. Now, if you look at this, this is a legend for the colors. It tells you, red being acidic, blue being basic. No surprise here. I just added sodium hydroxide to this. This is a base. Sodium hydroxide is a strong base. And the pH is around 9, it looks like, from here. Okay, about 9. Now, I'm going to add 2-bromo, 2-methyl propane. This compound right here. The reason we do these demos is to show you that this isn't just drawing on a board. This is a real thing. This liquid in here is 2-bromo, 2-methyl propane. It smells a little bit like, gasoline or turpentine or some other organic compound. I'll take a little bit of that. I'm going to add some drops to it. How many do I need? 10. Okay. Now, keep your eye on it. What's happening right now is this OH group is adding on or taking the place of bromine. When all of that OH is gone, what's going to happen to the pH of this compound? Is it still going to be basic? Well, it's certainly not going to be basic. So that's all we care about. Whether it becomes an acid or not, we don't know. But we're certainly going to see that the color should change. And I think it will, so keep your eye on it. It happens pretty suddenly, so you can't take your eyes off it. And it's about to happen. Keep your eyes on it. Is it better with a white background or a dark background? I don't know. We'll try a white background for the viewers at home. Watch out! What? Just like that. Isn't that cool? I think it's better with the white background, but whatever. I can say, well, okay, if you use up all the sodium hydroxide, let's add a little bit more, see what happens. It's back to being blue, but sure enough, very quickly, as long as I have enough of that other stuff left over there, it'll react, and don't wait for it. Wait, don't miss it. Don't miss it this time. Woo! It's like it glows, isn't it? Pretty cool. All right. So, again, the reason for demos, obviously, I'm turning the light off. Front light.
To make pretty colors.
Yeah, to make pretty colors. That's the main reason. Obviously, we like pretty colors. But also to illustrate what we're doing in the notes, but to show you that these things actually exist. These organic compounds aren't just drawings on a board. All right. Did you all finish this one yet, or no? Need some more time?
Yeah. Yes.
All right, let's do this. Where do you think that OH is going to go if he's replacing this bromine?
In the same spot.
I hope you're going to put him in the same spot. Yes. And what else would be formed over here? My fault. Yeah, it's an OH. And this would be an ABO. And that's the OH down there. Okay?
And what would you name that one?
And what's the name in a row? We'll go one at a time. What would I call... Draw that a little bit. What would I call this guy over here first?
2-methyl 2-bromo.
2-methyl 2-bromo. Propane. It's what the pros feel when they get hurt. Propane.
And then this
We
one
already
is
made that joke.
Alright.
Here.
2-methyl
2-propanol.
2-propanol is correct. Alright? 2-methyl 2-propanol. Good.
So we have to put. No, we don't need it.
You don't. But again, I don't really care about that as much. You would kind of pronounce it propanol, which is, it doesn't even sound right.
Okay.
All right. I'm going to stop this.